Okay, welcome back, guys. Okay, so let us discuss today about intuition behind generating functions. Okay, so we will talk about generating functions, and this is part one of the series of generating functions. Let us discuss the intuition. We all remember preparing for exams and we had to memorize a whole list of things and just produce it in the exam. And it's very hard to memorize such a list. For example, for my management exam, I had to remember the FIOL's 14 general administrative principles. So 14 principles, and it was very principles of general administrative theory, and it was very hard to remember. So in order to remember the content of the 14 principles, what I did was I encoded the points in a story, and I related the events happening in the story to the one of the principles of Fayol's principles, and that helped me encode or summarize the essential points of the principle into a way that is easy to remember. And if I remember that one story, I can uh, I can write the whole general administrative principle in the exam very well. So am I talking about this and how it is related to generating functions? So suppose there is a sequence of terms, there is a sequence of numbers, say 1, 1, 1, 1, so on, infinite till infinity 1. Now you want to remember this whole sequence. What was this sequence? In a way that if you give this encoded or short form of the sequence to someone, he can find any of the terms, or he knows the entire sequence if he knows this short summary of this whole sequence. The summary of this whole sequence is inside the generating function that generates this sequence. So which sequence generates this? Which closed form or summary, like the in the analogy, the story that helped me remember the files principle or the whole chapter, that compressed form of this sequence is nothing but the formula of infinite terms of a GP. That is 1 by 1 minus x is equals to, now inside this closed form you can generate the whole sequence, that is 1 plus 1 into x plus 1 into x square plus 1 into x cube plus so on. Okay, so this short formula, whoever mathematician sees this formula, he knows instantly the entire all the terms of the sequence, entire sequence, and he can find any general term or any rth term of the sequence as well. So this was an example, one of the example of the generating function that generates this infinite times one sequence. So we have multiple sequences, and for multiple sequences we can represent the essence of the sequence, or the short form or the summary of the sequence inside a formula. Okay, so that is the essence of generating functions. Okay, we will talk about it in detail in the next part of the videos. So let us understand what's the importance of this generating function, why are we even studying it. This generating function can be used for counting purposes as well in the real world. Let us see one question to understand how it can be used for counting. So this is one real world question. You have three lines and you have certain words on each line. So you can use only one word from each line. Okay, word or combination of word. Okay, this QU which is written together is to be considered as one unit. Okay, and you have to find uh, how many three-letter words can be used using only one entity from each line. For example, one three-lettered word could be S from the first line, A from the second, and D from the third line. Okay, so find the how do we find the total number of possible three-letter words or four-letter word or five-letter words that can be formed using only these three uh, lines? Okay, let us see that. So let us move on a new page. Okay, the first line was having Q, U, S and T. S and T. The second line was having A, I. The third line was having D and CK. D and CK. Now, in how many ways can I choose one letter word from the first line? We are writing all possible letters that we can choose from the first line. So, one lettered words, two possible ways, right? This power of x is representing how many lettered word did, what is the length of the word. So x power 1 means one lettered word for choosing x, s, or x power 1 for choosing one lettered word t from the first line, and this is qu. Qu is two-letter word. So one way of choosing a two-lettered word. Okay. So we have written all possible ways that we can choose a letter from the first line. What size of word is forming. Okay. Now from the second line, we can choose either A, that is a one-letter word in one way, or I. So that is also a one-letter word. These powers are representing, if you choose that unit, what is the length of the word that is being formed. And from third line, you can choose either a one-lettered word D in one way or a two-lettered word CK. So this would be x power 2. This would be x power 2. So if you, uh, what is this polynomial representing? This is representing all possible ways you can form all possible size lettered word. For example, if we simplify this, we will get 2x power 1 plus x square, then x power 1 plus x power 1, that is 2x power 1, 2x power 1, and this is representing x square plus x power 1. So if you select the any one lettered word from the first line, that is 2x power 1, two ways you can select a one lettered word, into from the second line you can choose a one lettered word. So total 2 into 2, 4x power 2, that is four ways you can choose a two lettered word from first line and the second line. And from the third line, you can choose a one-lettered word or a two-lettered word. So if you multiply, or if you open this polynomial and multiply all the terms, you will get a series. See, x square can be multiplied with 1 and 1. Okay, let's first see how many three-lettered words can be formed. Okay, so okay. Let us see four-lettered word. We cannot form three-lettered word. We have to pick exactly one unit from each line. There is no term for x power 0 in any of the lines. So, minimum a one-lettered word can be chosen from each line. So, minimum size would be x power 1, x power 1, x power 1. Okay. Okay, that's a three letter word, sorry. So that would be 2 into 2 into 1. So that will be 4x power 1 plus 1 plus 1, 3. This is four ways we can form three lettered words. Okay. And if I choose uh, x square from the first line, that is two lettered word, then plus 1, this would be a three lettered word, and from here we can choose another one, so 2 3 4. So that would be 2x ki power 2 3 4. This is these many four lettered words. Yeah, or we can choose two lettered words from here and two lettered word from the third line. So 2 plus 2 is 4 and plus 1 5. So 2x ki power 5. These many five lettered words we can make. Okay, 4 from can come from x power 1, x power 1, 2 plus 2 as well, right? Have we counted this? Um, yeah, we have counted this. X square 2, 3, 4. No, we have not counted this. 2, 2, 2 to the 4. Yeah, we have not counted it. Enough. 4, 5, 6, 6. This would be 6. Yeah, this would be 6 possible 4-lettered words. One possible is x power 2, 3, 4 from here, that is 2. And 1 from 2, 2 is a 4. Yeah, 6 x 4-lettered words can be formed from here. So this coefficient is representing how many ways we can form three-lettered word. This power is representing how many lettered words you can make picking one unit from each line. 6 ways we can make 4-lettered words from the three lines, and in 2 ways we can make 5-lettered words from picking words from each line, one unit from each line. So this is what the generating function intuition is in real world. And how do you think when you should use generating functions for counting is if you have groups, means you have three parts or three sections, and how many ways, all possible ways you can choose one unit from each of the group is when you should think of using generating functions. Okay, so that's all for this video part 1. Thank you for watching, and keep thinking, keep looking for new examples of mathematics in everyday life. And please like, share and subscribe to my channel, and take care and bye bye.